What if I told you there's an explosion so powerful it makes supernova look like firecrackers? Picture this, a burst of energy so colossal, it outshines entire galaxies for a fleeting moment, tearing through the fabric of space with unimaginable force. This isn't science fiction. This is a hypernova, the universe's most violent and rare cataclysm, a cosmic fireworks show gone rogue. These events are so extreme, they defy everything we thought we knew about stellar explosions. And today, we're diving deep into their mind-bending secrets. Imagine a star, not just any star, but a behemoth dozens of times more massive than our Sun. When these giants reach the end of their lives, they don't just fade away. They detonate with a fury so intense it ripples across the cosmos. A hypernova isn't merely a bigger supernova, it's a whole different beast. The energy released in seconds rivals what our Sun will produce over its entire lifetime. Gamma-ray bursts, jets of matter moving at nearly the speed of light, temperatures so high they make nuclear bombs seem lukewarm. This is the chaos unleashed when a hypernova erupts. And yet, despite their terrifying power, these explosions are vanishingly rare, occurring maybe once every few 100,000 years in a galaxy like ours. That rarity makes them even more fascinating. Catching one in action is like winning the cosmic lottery. But here's what really blows scientists' minds. Hypernova might hold the keys to some of the universe's greatest mysteries. How did the first stars die? Where do heavy elements like gold and platinum come from? Could these explosions have shaped the evolution of galaxies? Each hypernova is a time capsule, a glimpse into the universe's most extreme conditions. And as we uncover their secrets, we're rewriting the story of the cosmos itself. So buckle up. Over the next 30 facts, we'll explore the sheer scale, the mind-bending physics, and the unanswered questions surrounding these colossal explosions. By the end, you'll see the universe in a whole new light, one where even supernova are just the opening act. To put the staggering power of a hypernova into perspective, think about the Sun, our steady, life-giving star that has shone for billions of years. Now imagine all the energy it will ever produce, squeezed into just a few seconds. That's the scale we're talking about. Hypernova don't just surpass supernova, they dwarf them, unleashing up to 100 times more energy in their apocalyptic blast. While a typical supernova might outshine its host galaxy for weeks, a hypernova does something even more extreme. For a brief, blinding moment, it can outshine the combined light of every star in the observable universe. The numbers are incomprehensible. We're talking about temperatures hotter than a billion suns, shockwaves racing outward at nearly the speed of light, and enough raw power to reshape entire regions of space. One of the most telling signatures of a hypernova, gamma-ray bursts the universe's most luminous electromagnetic explosions. These beams of high-energy radiation are so intense they can pierce through galaxies, leaving a trail of devastation in their wake. If one were to occur nearby, even thousands of light-years away, it could strip Earth's ozone layer and trigger a mass extinction. The fact that we've detected these bursts from the edges of the cosmos speaks volumes about their incomprehensible energy. They're like cosmic lighthouses, signaling the birth of black holes and the deaths of the universe's mightiest stars. But what makes hypernova so much more extreme than their supernova cousins? It comes down to the stars that create them. While a supernova might arise from a star 20 or 30 times the mass of our Sun, hypernova require true monsters, stellar titans 50 times heavier or more. These are rare, short-lived beasts, burning through their fuel in just a few million years before detonating in a way that obliterates the usual rules of stellar death. Instead of collapsing inward and rebounding as a supernova, these stars experience a phenomenon called collapsar formation, where their cores implode directly into a black hole while the outer layers are ejected in an ultra-relativistic jet. It's this jet, narrow but unimaginably powerful, that gives rise to the gamma-ray burst and the hypernova's signature extreme brightness. Scientists believe hypernova might be responsible for seeding the universe with some of the heaviest elements like gold, platinum, and uranium. In the furnace of these explosions, atoms are forged under conditions so extreme they defy laboratory reproduction. Without hypernova, the periodic table would look very different, and so might we. Every time you look at a piece of jewelry or hold a smartphone, you're holding remnants of cosmic cataclysms that happened billions of years ago. That's the legacy of hypernova, not just destruction, but creation on a scale we're only beginning to understand. At the heart of every hypernova lies one of the universe's most enigmatic creations, a newborn black hole. When a star 30 times more massive than our Sun exhausts its nuclear fuel, its core doesn't just collapse, it free falls into oblivion. Gravity wins in an instant, compressing matter so densely that not even light can escape. But unlike a typical supernova, where the explosion blows the outer layers into space, a hypernova's collapse is far more violent and asymmetric. This is where the collapsar model comes into play. Imagine a star spinning so fast its core flattens into a disk as it implodes. That rapid rotation channels the energy of the collapse into twin jets, spewing matter at near light speed like cosmic blowtorches. These jets are the engines behind the hypernova's terrifying brilliance and the gamma-ray bursts we detect across the universe. The birth of a black hole during a hypernova isn't a quiet event. It's a cosmic demolition job. As the star's core crushes itself into a singularity, the outer layers rebound off this newly formed black hole in a shockwave of unimaginable force. But here's the twist: without that rapid spin, you just get a supernova. It's the star's rotation that transforms a catastrophic collapse into a hypernova. Think of it like water spiraling down a drain. The faster it spins, the more focused and energetic the outflow becomes. In hypernova, that spin turns a spherical explosion into focused jets capable of punching through the star's remaining structure, creating the narrow, ultra-powerful beams we observe as gamma-ray bursts. What's left behind tells its own story. While supernova often leave dense neutron stars, hypernova almost always forge something far more extreme: stellar mass black holes. These aren't the supermassive monsters at the center of galaxies, but they're smaller, equally fascinating cousins. With masses between 5 and 50 times that of our Sun, they're the gravitational tombstones of the universe's mightiest stars. Some even get kicked away at high speeds by the asymmetrical explosion, becoming rogue black holes drifting unseen through the galaxy. The collapsar model explains why hypernova are so rare. Only the most massive, rapidly spinning stars can produce them, a combination as uncommon as it is spectacular. When these stars die, they don't just leave behind a black hole, they fundamentally alter their surroundings. The jets inject so much energy into nearby gas clouds that they can trigger new star formation, effectively turning destruction into creation. It's a reminder that even in the universe's most violent moments, there's a strange kind of order, a balance between chaos and the birth of new cosmic wonders. The connection between hypernova and gamma-ray bursts is one of the most thrilling detective stories in modern astronomy. While most cosmic explosions fade quickly, hypernova announce their presence with a signature fireworks display, long gamma-ray bursts or GRB that can last anywhere from 2 seconds to several minutes. These aren't just random flickers in the darkness, they're the death screams of the universe's most massive stars, and their discovery reshaped our understanding of stellar catastrophes. Take GRB 990123, detected in January 1999. This wasn't just another burst, it was a revelation. For a fleeting moment, it outshone the rest of the universe combined in gamma rays, then left behind an afterglow so bright that amateur astronomers could spot it with backyard telescopes. That afterglow was the smoking gun, revealing the hypernova at its core. As telescopes swung into action, they captured something unprecedented. The explosion's light curve matched predictions for a collapsar, a rapidly spinning star collapsing straight into a black hole while blasting jets of plasma at near light speed. Those jets, focused into narrow beams by the star's rotation, were the source of the gamma-ray burst, like a cosmic lighthouse sweeping its beam across the universe. What makes long GRBs special isn't just their duration but their energy profile. Unlike short bursts, which often come from neutron-star collisions, long GRBs carry the unmistakable fingerprints of hypernova, spectral lines showing heavy elements like nickel and iron forged in the star's final moments. They also leave behind telltale remnants, expanding bubbles of ultra-hot gas and often a black hole lurking where a star once blazed. The afterglow of GRB 990123 lingered for weeks, giving scientists their first detailed look at the hypernova engine at work. The implications stretch far beyond a single explosion. Long GRBs act as cosmic measuring tapes, letting astronomers probe the early universe. Because their light travels so far, they illuminate galaxies billions of light years away, revealing conditions in the cosmos just a few 100 million years after the Big Bang. Some researchers even suspect these bursts could have influenced the evolution of life on Earth. A nearby hypernova, after all, would deliver a lethal dose of radiation, meaning these cataclysms might not just shape galaxies, but the fate of civilizations within them. Yet for all their destructive power, hypernova and their gamma-ray bursts are also cosmic forges. The same jets that produce GRBs carry newly minted heavy elements into interstellar space, enriching future generations of stars and planets. Every time we detect one of these bursts, we're glimpsing the universe's most extreme physics, a laboratory where matter, energy, and gravity collide in ways we're still struggling to comprehend. And with each discovery, we move closer to answering one of astronomy's biggest questions: how the most violent deaths in the cosmos give birth to the building blocks of everything we know. The universe's most lavish jewelry stores aren't found on Earth, they're scattered across the cosmos, forged in the heart of hypernova explosions. When these stellar titans detonate, they don't just unleash chaos, they become cosmic alchemists, transforming simple atoms into rare, precious elements. Take gold, for instance. That ring on your finger or the circuitry in your phone likely contains atoms born in a cataclysm so violent it defies imagination. Hypernova achieve this through a process called rapid neutron capture, or the R process, where atomic nuclei are bombarded with neutrons so fast they can't decay, building heavier and heavier elements in seconds. Under normal stellar conditions, creating gold or platinum would be impossible. It takes the extreme pressures and temperatures of a hypernova's debris field to cram neutrons into nuclei fast enough to forge these cosmic treasures. Picture the aftermath of the explosion, a swirling maelstrom of ultra-hot matter, neutron-rich material ejected at relativistic speeds. In this environment, atomic nuclei act like snowballs rolling downhill, gathering neutrons with every collision. The R process doesn't just sprinkle heavy elements into space, it floods entire regions with them. A single hypernova can produce more gold in moments than humanity has mined in all of history. These elements then hitch rides on stellar winds and shockwaves, eventually finding their way into interstellar clouds that collapse into new stars, and billions of years later into planets like Earth. Scientists trace Earth's gold back to such cataclysms by studying isotopic signatures, chemical fingerprints that reveal an element's origin. Gold formed in the R process has a distinct neutron-to-proton ratio, different from elements created in supernova or neutron star mergers. When researchers analyzed ancient meteorites, they found gold's isotopic signature matched hypernova models almost perfectly. That means the gold in your watch or Olympic medal might be stardust twice over. First forged in a dying star's furnace, then scattered across the galaxy by a hypernova's fury. But gold is just one piece of the puzzle. The R process also creates platinum, uranium, and other heavy elements essential to modern technology. Without hypernova, the periodic table would stop at iron, leaving the universe chemically impoverished. These explosions don't just destroy, they're the ultimate recyclers, turning doomed stars into the building blocks of planets' life and even the devices you're using right now. Every time you hold something made of precious metal, you're holding a relic of one of the cosmos's most spectacular events, a hypernova's final, glittering gift to the universe. Spotting a hypernova in action is like witnessing a lightning strike in a desert so rare you might wait lifetimes and still miss it. In a galaxy the size of the Milky Way, these cosmic detonations occur just once every 100,000 years, making them some of the most elusive events in the universe. Compare that to regular supernovae, which light up our galactic neighborhood every few decades, and you start to grasp why researchers treat each hypernova discovery like striking scientific gold. The first confirmed observation came in 1998 with SN 1998 BW, a cataclysm so extraordinary it rewrote the textbook on stellar explosions. This wasn't just another supernova. SN 1998 BW erupted with 10 times the energy of a typical stellar explosion, and its light curve, the way its brightness evolved over time, matched no known category. Astronomers quickly realized they'd found something unprecedented. The explosion's aftermath revealed signatures of a collapsar in action, a black hole birth paired with relativistic jets, the hallmarks of a true hypernova. What made this detection even more remarkable was its proximity, relatively speaking at least. Nestled in the galaxy ISO 184 G82, about 140 million light-years away, it was close enough for telescopes to capture unprecedented details. For the first time, scientists had front-row seats to a hypernova's fury. Detecting these events isn't just about luck, it's a technological marathon. Hypernova fade fast, and their most telling features like gamma-ray bursts last mere seconds. Without satellites like NASA, a swift observatory scanning the skies around the clock, we'd miss most of them entirely. Even then, confirmation often requires a global effort. When a potential hypernova triggers an alert, telescopes worldwide pivot to observe its afterglow, analyzing light across the electromagnetic spectrum. The data must be pieced together like a cosmic jigsaw puzzle, distinguishing hypernova from their less explosive cousins. Yet every challenge makes discoveries like SN 1998 BW even more valuable. Each hypernova observed peels back another layer of mystery, offering clues about how the universe's heaviest elements spread and how black holes form. And with next-generation instruments like the Vera Rubin Observatory coming online, our chances of catching these cosmic unicorns are improving. Every new detection brings us closer to answering a tantalizing question. In a universe teeming with explosions, what other extremes are we yet to witness? The terrifying reality about hypernova isn't just their raw power, it's their ability to erase life across interstellar distances. Within 1,000 light-years of one of these explosions, planets orbit in what scientists grimly call the death zone, where gamma-ray bursts act like cosmic blowtorches, searing away atmospheres and sterilizing entire worlds. These aren't hypothetical dangers. Geological records suggest Earth may have narrowly avoided catastrophe 2.5 million years ago, when a hypernova candidate, the ancient star HD 199534, may have bathed our planet in radiation. While not close enough to trigger mass extinction, its gamma-ray pulse could still have subtly altered Earth's climate, proving even distant hypernova leave fingerprints on biological history. Picture the mechanics of this cosmic sterilization. When a hypernova's gamma-ray jets strike a planet, they don't just deliver radiation, they rewrite chemistry. The initial blast ionizes atmospheric nitrogen and oxygen, sparking chain reactions that produce nitrogen dioxide, a compound that ravages ozone layers. Without that protective shield, ultraviolet radiation from the planet's own star pores in unchecked, devastating ecosystems, marine plankton, the foundation of aquatic food chains, would perish first, collapsing fisheries within years. Land plants would follow, their DNA shredded by UV overload. The grim irony: hypernova might create the heavy elements necessary for life while simultaneously snuffing it out across light years of space. Astrobiologists model these scenarios using Earth's worst extinction events as benchmarks. The late Ordovician mass extinction, 445 million years ago, wiped out 85% of marine species, and some researchers argue its timing aligns suspiciously with a potential nearby gamma-ray burst. Sedimentary layers from that period show abrupt spikes in ultraviolet-sensitive mutations among surviving species, hinting at ozone depletion. While the evidence isn't conclusive, it paints a chilling picture. Hypernova could be silent assassins in the cosmic dark, their lethal radiation arriving without warning to reshape biospheres. Yet there's a bizarre silver lining. The same radiation that sterilizes might also jumpstart life's chemical precursors. Laboratory experiments show gamma rays can trigger the formation of amino acids in primordial soups, suggesting hypernova could paradoxically both destroy and enable life. It's a reminder of the universe's brutal duality. The forces that obliterate worlds also scatter the seeds for new ones. Every hypernova is a roll of the cosmic dice, capable of ending civilizations in one galaxy while possibly nurturing them in another. For now, Earth seems to occupy a fortunate middle ground. The Milky Way's last known hypernova, in the constellation Cygnus, occurred 12,000 light-years away, close enough for astronomers to study its remnants, but safely beyond the death zone. Still, as we discover more of these stellar time bombs lurking in our galactic neighborhood, one unsettling question lingers. Could humanity's reign end not with climate collapse or nuclear war, but with a flash of gamma rays from a dying star we never even saw coming? While supernovae often leave behind beautifully symmetrical remnants like the Crab Nebula, hypernova shatter that expectation with explosions so lopsided they seem to defy physics. The key difference lies in the engine driving the chaos, where a typical supernova detonates outward in all directions. A hypernova channels its apocalyptic energy into narrow, ultra-fast jets spewing from its poles. These aren't gentle outflows. We're talking about beams of plasma screaming through space at 99% the speed of light, carrying enough energy to punch through the dying star's outer layers like a bullet through tissue paper. This jet-driven violence leaves a distinct fingerprint. Instead of a round, expanding shell, hypernova remnants often look like hourglasses or bipolar nebulae, structures stretched and twisted by those relativistic jets. Take the case of supernova remnant W49b, a messy, elongated wreckage field in our galaxy. X-ray observations reveal iron-rich material concentrated along two opposing axes, the smoking gun of polar outflows. Meanwhile, radio telescopes detect lobes of energized particles far from the explosion's center, evidence that the jets kept raging long after the initial blast. Why such asymmetry? It all comes down to rotation. Hypernova progenitors spin so fast their cores flatten into disks during collapse, acting like cosmic particle accelerators. As matter spirals into the newborn black hole, magnetic fields coil into springs, launching material along the spin axis like a celestial slingshot. The result is a directional explosion where most of the energy and the heavy elements forged in the blast get funneled into those twin beams. Anything not in the jet's path gets left behind, creating bizarre, uneven debris fields that puzzle astronomers. The aftermath challenges our understanding of stellar deaths. While spherical supernovae distribute elements evenly, hypernova spray their cosmic riches in focused streams, potentially leaving entire regions of galaxies enriched while others remain barren. This might explain why some ancient star clusters show bizarre chemical patches, hypernova's lopsided debris frozen in time. It's a reminder that in the universe's most extreme physics, symmetry is a luxury few explosions can afford. Deep within the fury of a hypernova, nature operates its own version of the Large Hadron Collider, but on a scale that makes our most advanced particle accelerators look like toys. These cosmic explosions don't just blast matter into space, they turn shock waves into natural supercolliders, propelling subatomic particles to energies so extreme they defy terrestrial physics. When a hypernova's supersonic shockwave plows through surrounding gas and dust, it doesn't just heat material, it electrifies it, creating chaotic electromagnetic fields that whip protons and electrons to nearly light speed. The process, known as Fermi acceleration, acts like a cosmic ping-pong match, with particles ricocheting between magnetic shock fronts until they're hurled into space with incomprehensible force. The numbers are staggering. While human-built accelerators like CERN LHC can boost protons to tera-electronvolt energies, hypernova shocks routinely reach petaelectronvolt levels thousands of times more powerful. Some of these accelerated particles become cosmic rays that streak across the galaxy, eventually raining down on Earth as high-energy messengers from distant cataclysms. In 2017, the IceCube Neutrino Observatory in Antarctica detected a neutrino with energy comparable to a well-thrown baseball, all packed into a single subatomic particle. Tracing its path led astronomers straight back to a blazar 4 billion light-years away, proving such extreme energies originate in cosmic accelerators like hypernova. How does this alchemy work? Imagine the explosion's shockwave as a moving wall of pure violence expanding at millions of miles per hour, compressing interstellar material until magnetic fields tangle into knotted ropes. Charged particles get trapped in these magnetic whirlwinds, bouncing back and forth like pinballs while gaining speed with each collision. Over time, the luckiest particles escape the chaos, ejected with enough energy to cross intergalactic distances. These aren't just stray electrons. Hypernova can hurl entire atomic nuclei from helium to iron at velocities approaching light speed. When such particles finally collide with Earth's atmosphere, they spawn particle showers so vast they can span continents. Yet neutrinos remain the holy grail of hypernova physics. Unlike cosmic rays, which get deflected by magnetic fields during their journey, neutrinos fly straight from their source like microscopic arrows. Detecting them offers an unobstructed view into the explosion's heart specifically, the moment its collapsing core becomes a black hole. During that critical phase, neutrino emissions briefly outshine the entire visible universe, carrying secrets about matter under conditions so extreme they can't be replicated on Earth. Some theories suggest hypernova might even produce sterile neutrinos, hypothetical particles that could explain dark matter. Every time one of these ghostly particles zips through our detectors, it's like receiving a postcard from the universe's most extreme particle physics lab, written in a language we're still learning to decode. The implications stretch beyond astronomy. By studying hypernova-accelerated particles, scientists gain insights into radiation hazards for future space travelers, or even clues about how cosmic rays might have influenced mutations in Earth's evolutionary history. These explosions don't just destroy stars, they fuel an invisible rain of high-energy particles that has been shaping the cosmos since the first hypernova lit up the infant universe. And with every neutrino detection or ultra-high-energy cosmic ray we trace back to its source, we're piecing together a deeper truth. The universe's most violent events are also its most ingenious laboratories, forging and flinging particles in ways we're only beginning to comprehend. Not all hypernova explode with the same cosmic recipe. Some blast apart with hardly any hydrogen left, like a firework that's already burned through its outer shell before detonating. These stripped-down explosions fall into a special category called Type I hypernova, and they're the universe's ultimate high-stakes gamblers. The stars behind them don't just die, they go all in, shedding their outer layers long before the final show begins. The key to understanding these hydrogen-poor explosions lies in their progenitors, Wolf-Rayet stars, often nicknamed WR stars. Imagine stellar giants so massive and volatile, their own radiation blasts away their outer hydrogen envelopes like a cosmic sandstorm eroding a mountain. These stars aren't just big, they're fast-living, fast-dying powerhouses, expelling gas at millions of miles per hour through winds more violent than any hurricane. By the time a WR star reaches its cataclysmic end, its outer layers have already been stripped bare, leaving behind a naked core of helium, carbon, and oxygen. When this core collapses, the resulting hypernova isn't just powerful, it's chemically distinct, lacking the hydrogen signatures seen in more traditional supernovae. Take SN 2002 AP, one of the most studied type I hypernova on record. When it lit up a galaxy 760 million light-years away, telescopes caught something peculiar. Its spectrum showed almost no hydrogen, but it shone 10 times brighter than a typical supernova. This wasn't just a star exploding, it was a star that had already bared its soul before the final detonation. The event matched predictions for a WR star's demise, where years of relentless stellar winds had peeled away its outer layers like an onion losing its skin. The implications go beyond just classification. Hydrogen-deprived hypernova like these are prime suspects for producing long gamma-ray bursts, those universe-spanning explosions we discussed earlier. Why, without an outer hydrogen blanket to smother the blast, the star's death throes can channel energy into ultra-focused jets more easily. It's the difference between a firecracker wrapped in wet paper versus one packed in a metal pipe. One fizzles while the other becomes a high-velocity projectile. But WR stars don't just vanish quietly after shedding their layers. Their pre-explosion winds create vast, glowing nebulas called Wolf-Rayet bubbles, structures we've spotted around suspected hypernova progenitors in our own galaxy, like the infamous star WR104. These bubbles act as cosmic breadcrumbs, letting astronomers trace where the next type I hypernova might occur. Yet even with these clues, predicting one remains nearly impossible. WR stars live fast, die young, and leave behind some of the most spectacular and chemically unique explosions in the cosmos. What makes type I hypernova so fascinating isn't just what they lack, but what they reveal. Their absence of hydrogen tells a story of stellar evolution pushed to extremes, where only the most massive, volatile stars can burn through their outer layers before exploding. And in their wreckage, they leave behind heavy elements forged under conditions so extreme, they rewrite our understanding of stellar chemistry. Every time we spot one of these hydrogen-free cataclysms, we're glimpsing the final act of a star that spent its life defying expectations only to die in a way that lights up the universe. Among the bizarre remnants a hypernova can leave behind, none are stranger or more terrifying than magnetars. Imagine a neutron star, already one of the densest objects in the universe, cranked up to 11 with a magnetic field so intense it could erase your credit cards from halfway across the galaxy. These cosmic anomalies are the universe's ultimate electromagnets, born from hypernova so violent they imprint their chaos onto the stellar corpse left behind. Take SGR 180620, a magnetar nestled in the constellation Sagittarius. On December 27, 2004, it unleashed a gamma-ray flare so powerful it briefly outshone the full moon, despite being 50,000 light-years away. For a fifth of a second, this object released more energy than the Sun does in 250,000 years. The blast was so fierce it actually compressed Earth's ionosphere, temporarily disrupting radio communications worldwide. Scientists later determined the flare likely originated from a starquake, a catastrophic rupture in the magnetar's crust caused by its unimaginably twisted magnetic fields. But how does a hypernova forge something this extreme? It starts with the star's collapse. When a particularly massive star explodes as a hypernova, its core doesn't just contract into a neutron star. It does so while rotating at near light speeds and turbocharging its magnetic field through a process called dynamo amplification. Picture a dynamo on steroids. As the star's core implodes, its already intense magnetic field gets wound tighter and tighter, like a rubber band twisted until it snaps. The result, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's, enough to atomize molecules from 1,000 kilometers away. What makes magnetars even wilder is their unpredictability. Unlike pulsars, which emit steady beams of radiation, magnetars erupt sporadically with bursts of X-rays and gamma rays. Some, like SGR 180620, go dormant for decades before suddenly waking up in a fit of cosmic violence. These outbursts are thought to occur when the magnetar's ridged crust, under unimaginable stress from those magnetic fields, finally cracks, releasing pent-up energy like a seismic event on steroids. Yet magnetars might hold clues to even deeper mysteries. Some theorists suggest these hypernova remnants could be behind fast radio bursts, those enigmatic millisecond-long radio pulses detected across the universe. Others speculate their magnetic fields are so extreme, they twist the fabric of space-time itself, creating observable distortions. Every time one of these objects flares up, it's like the universe is running an experiment in conditions we could never replicate on Earth, a natural lab for physics at its most extreme. The legacy of a hypernova doesn't end with the explosion. In forging magnetars, these cataclysms leave behind objects that continue to reshape their surroundings long after the initial blast fades. They're proof that even in death, the universe's most massive stars refuse to go quietly, instead leaving behind magnetic monsters that keep challenging everything we think we know about the cosmos. Long before galaxies settled into their familiar shapes, hypernovae were the cosmic architects of change, violent, unpredictable, but essential to building the universe we know today. In the first chaotic billion years after the Big Bang, when the cosmos was little more than a sea of hydrogen and helium, these explosions acted like elemental sprinklers, blasting newly forged metals into the void. Without them, the universe would have remained a sterile wasteland, incapable of forming rocky planets or life as we know it. Take the earliest galaxies, fragile collections of gas struggling to ignite their first stars. When a hypernova erupted among them, it didn't just light up the darkness, it transformed the chemistry of entire galactic neighborhoods. The explosion's shockwaves plowed through pristine gas clouds, seeding them with carbon, oxygen, and iron elements that acted like cosmic antifreeze. How simple atoms like hydrogen clump together inefficiently, but sprinkle in some heavier elements, and suddenly gas clouds can cool faster, collapse more easily, and birth new generations of stars. This recycling of stellar ash into star-forming fuel is why astronomers call hypernova the universe's first fertilizer. Evidence for this comes from some of the most distant galaxies ever observed. When telescopes like Hubble and JWST peer back in time, they spot galaxies from just 700 million years after the Big Bang, yet some already contain traces of heavy elements. The only explanation, hypernova had already been at work, polluting the cosmos with metals barely a few 100 million years after the first stars flickered to life. These weren't gentle enrichments. Imagine a tsunami of superheated gas carrying enough iron to mint 1 trillion Earth cores, scattering it across light years of space in a single catastrophic event. But hypernova didn't just spray metals randomly, they distributed them unevenly, creating pockets of varying chemistry. Modern galaxy simulations show this patchiness was crucial. Regions dosed with hypernova debris formed denser, faster-cooling stars, while untouched areas remained stagnant. This might explain why some ancient star clusters, like those in the Milky Way's halo, show wild variations in metal content even though they formed around the same time. Hypernova essentially set the table for galactic diversity, ensuring the universe wouldn't evolve uniformly. The most fascinating twist, these explosions might have dictated the size and structure of galaxies themselves. When a hypernova's jets ripped through primordial gas clouds, they didn't just enrich, they heated. That extra heat raised the pressure in star-forming regions, preventing small galaxies from growing too dense too quickly. Without hypernova's tempering influence, early dwarf galaxies might have burned through their fuel in frenzied starbursts, leaving no material to build giants like the Milky Way. It's a cosmic balancing act. Too few hypernova, and galaxies stay small and metal poor. Too many, and they overheat and stall. The fact that we exist at all suggests the universe, by some miracle, got the recipe just right. Most stellar explosions fade predictably, a brilliant peak followed by a steady decline. Hypernova laugh at that simplicity. Their light curves, graphs tracking brightness over time, don't just bend the rules, they rewrite them. While a typical supernova might dim by half in weeks, hypernova cling to their glory, remaining luminous for months thanks to a radioactive powerhouse, nickel-56. This unstable isotope, forged in the explosion's heart, decays into cobalt-56 and then iron, releasing gamma rays that heat the expanding debris. But here's the twist: hypernova produce so much nickel-56, their glow lasts far longer. SN 2006 Gi, one of the brightest ever recorded, stayed visible for nearly a year because its explosion synthesized an astonishing 20 solar masses of nickel, enough to outshine entire galaxies as it slowly decayed. Yet nickel isn't the only actor in this prolonged light show. Hypernova often erupt within thick shrouds of gas expelled by their progenitor stars before death. When the explosion's shockwave slams into this circumstellar material, it doesn't just fade, it reignites. The collision converts kinetic energy into light, creating secondary brightness peaks that baffled astronomers for decades. Take SN 2010 JL, a hypernova in galaxy UGC 5189. Its light curve didn't follow the smooth radioactive decay expected. Instead, it surged again 90 days post-explosion as the shockwave plowed through a cocoon of gas equal to 15 suns. This delayed brilliance acts like a cosmic echo, revealing how hypernova progenitors live violently long before they die. The aftermath holds even more surprises. While supernova remnants cool predictably, hypernova debris can exhibit temperature plateaus, periods where the fading stalls because shock-heated gas keeps pumping energy into the system. It's the difference between a campfire dying to embers versus one that gets fresh logs tossed in periodically. These plateaus, lasting weeks or months, leave spectral fingerprints showing oxygen and calcium glowing fiercely long after the explosion. What makes hypernova light curves so valuable isn't just their defiance of norms, their cosmic Rosetta Stones. Their prolonged brightness lets astronomers track how heavy elements mix and spread, while shock interactions reveal the final, turbulent years of the progenitor star. Every anomalous bump or extended fade tells a story of a star that didn't just explode, but roared its departure across the cosmos in slow motion. Some of the most mysterious gamma-ray bursts aren't the bright, flashy ones we easily spot. They're the cosmic ghosts, events so shrouded in dust that their visible light gets smothered before reaching our telescopes. These dark bursts, first identified by NASA's Swift satellite, reveal themselves only through faint X-ray or gamma-ray whispers, forcing astronomers to play interstellar detective to uncover their hypernova origins. Take GRB 070306, a burst detected in March 2007. While its gamma-ray signal lit up Swift's sensors like a flare, follow-up observations found nothing in visible light, just an eerie absence where a hypernova's afterglow should have been. The culprit, a thick cocoon of dust around the dying star, absorbing nearly all visible photons while letting high-energy radiation slip through. This dust isn't just a nuisance, it's a time capsule. Hypernova exploding in star-forming regions often churn out immense dust clouds as their outer layers cool and fragment. When the blast occurs inside such a shroud, the result is a gamma-ray burst without its usual visual fireworks. The swift satellite's ability to rapidly pivot toward these events has been revolutionary, capturing X-ray afterglows that hint at the hidden violence beneath. In some cases, like GRB 120422a, infrared telescopes later pierced the dust veil, revealing a hypernova's heat signature glowing dimly like an ember in a smoke-filled room. The implications stretch beyond mere obscuration. Dark bursts suggest hypernova might be even more common than we thought. We're simply missing the ones cloaked in cosmic soot. They also challenge how we map stellar deaths. If a hypernova explodes in a dusty galaxy and no one sees it, does it still shape the universe? The answer, thanks to Swift's X-ray vision, is a resounding yes. These hidden explosions still pump heavy elements and energy into space, their influence felt long after the dust settles. Perhaps the most tantalizing dark burst is GRB 080319b, nicknamed the Naked Burst for its near-total lack of afterglow. For weeks, astronomers scoured its coordinates, finding nothing until the Hubble Space Telescope detected an ultra-faint smudge, a galaxy so dusty, it dimmed the hypernova's light by a factor of 10,000. This wasn't just an obscured event, it was a hypernova screaming into a pillow, its energy almost entirely trapped. Cases like these force us to reconsider where hypernova might lurk, reminding us that the cosmos still holds explosions we've yet to properly see, only infer from their faintest, most stubborn echoes. The destructive fury of a hypernova doesn't just end with annihilation, it sparks creation. These explosions unleash shockwaves so powerful they act like cosmic sculptors, carving through nearby gas clouds and compressing them into dense knots where new stars are born. It's a paradox of the universe. The same force that tears a star apart can also lay the groundwork for new ones. Nowhere is this more evident than in the Carina Nebula, a stellar nursery 7,500 light-years away, where ancient hypernova may have set the stage for the dazzling star clusters we see today. Picture the aftermath of a hypernova's detonation. As the blast wave expands at millions of miles per hour, it slams into surrounding molecular clouds, immense regions of cold gas and dust drifting between stars. The shock front doesn't just pass through, it squeezes. Like a snowplow piling up drifts, the wave's pressure triggers instabilities in the cloud, causing pockets of gas to collapse under their own gravity. These compressed regions, now denser and hotter, reach a critical threshold where nuclear fusion ignites. Voila, a new star flickers to life, its birth catalyzed by a cataclysm light-years away. The Carina Nebula offers a textbook example. This sprawling, star-forming region is home to Eta Carinii, a volatile binary system that could one day produce a hypernova. But it's the nebula's past that tells the real story. Astronomers studying its intricate pillars and bubbles have found chemical signatures like enhanced iron and nickel consistent with ancient hypernova debris. Even more telling, the nebula's youngest star clusters align along shockfront patterns, as if their formation was triggered by some long-ago explosion. The timing fits. Computer simulations show a hypernova blast wave could have swept through Carina's gas clouds around 2 million years ago, compressing them just enough to spark the birth of stars like Trumpler 14, a glittering cluster of massive young suns. But hypernova don't just kickstart any stars, they favor the giants. The most massive stars form fastest in these shock-compressed environments, meaning hypernova-triggered nurseries tend to produce heavyweight stars destined for explosive deaths of their own. It's a self-perpetuating cycle. Hypernova beget massive stars, which eventually explode as hypernova, birthing more stars in turn. This might explain why some galaxies, like the starburst galaxy M82, show hypernova remnants nestled right next to bustling stellar nurseries. The explosions are literally shaping the next generation. The implications stretch beyond single nebulas. On a galactic scale, hypernova shockwaves could explain why star formation isn't uniform. Some regions burst with young stars while others lie dormant. By seeding clouds with heavy elements and compression, hypernova might act as cosmic pacemakers, regulating where and when galaxies light up with new stars. Even our solar system's birth could trace back to such an event. Isotopic ratios in meteorites hint that a nearby explosion, perhaps a hypernova, enriched the primordial cloud that became our sun and planets. So while hypernovae are engines of destruction, they're also midwives to creation. Every time one detonates, it doesn't just erase a star, it scatters the seeds for countless others, ensuring the cosmos never runs out of new suns to light the darkness. Among the universe's most violent explosions, hypernovae serve an unexpected role: cosmic yardsticks. While their eruptions seem chaotic, certain types exhibit remarkable consistency in their peak brightness, particularly Type I hypernova stripped of hydrogen and helium. This uniformity turns them into invaluable tools for measuring the vast stretches of space, helping astronomers tackle one of cosmology's greatest challenges: pinning down the Hubble constant, the rate at which the universe expands. The principle is elegant in its simplicity. Just as you can estimate a lighthouse's distance by comparing its known brightness to how dim it appears from afar, astronomers use hypernova as standardizable candles. Type I hypernova, despite their explosive differences, follow a pattern. Their luminosity correlates tightly with how quickly their light curves fade after peaking. The slower the fade, the brighter the explosion. By measuring this decay rate, scientists can calculate the hypernova's intrinsic brightness, then compare it to its observed brightness from Earth to determine its distance. This method, refined over decades, offers a crucial cross-check against other distance measuring techniques like Cepheid variables or the cosmic microwave background. The stakes couldn't be higher. Discrepancies in the Hubble constant, measured differently through various methods, have sparked what astronomers call the cosmic tension. Space telescope data from nearby galaxies suggests an expansion rate of about 73 kilometers per second per megaparsec, while observations of the early universe's afterglow peg it closer to 67. Hypernova help bridge this gap. In 2019, a team using Type I hypernova in relatively nearby galaxies landed on a value of 75.5, leaning toward the faster expansion camp. Each new hypernova measurement sharpens our cosmic ruler, testing whether the tension stems from measurement errors or hints at undiscovered physics, like dark energy evolving over time. What makes hypernova especially valuable is their reach. Unlike Cepheids, which fade into invisibility beyond a few 100 million light-years, hypernova remain detectable across billions. The record holder, SN 2002 AP, was spotted 760 million light-years away with a brightness that matched its expected peak once corrected for its light curve's decay rate. This extended range lets astronomers map the universe's expansion across different epochs, tracing how dark energy's influence may have changed over cosmic history. Yet the method isn't foolproof. Dust in distant galaxies can dim hypernova, skewing distance calculations. That's where multi-wavelength observations come in. By studying the same explosion in radio, X-ray, and infrared, each wavelength affected differently by dust, researchers can correct for obscuration. The James Webb Space Telescope has been game-changing here, piercing dust clouds with its infrared eyes to validate hypernova distances that older telescopes might have misjudged. The broader implication: hypernova aren't just destroyers, they're cosmic cartographers. Every time one erupts, it illuminates the fabric of spacetime itself, offering clues to whether our universe's expansion will accelerate indefinitely, tear apart in a big rip, or someday reverse. For astronomers, that makes each explosion a beacon not just of stellar death, but of profound cosmological discovery. While most stellar explosions fade steadily, hypernova sometimes throw a curveball, a sudden, unexpected surge in brightness weeks or even months after the initial blast. These mysterious bumps in the light curve aren't random glitches. They're cosmic breadcrumbs revealing secrets about the star's life long before it exploded. Picture this: before its catastrophic end, a hypernova's progenitor star wasn't just sitting idle, it was shedding massive amounts of material in violent stellar winds. When the explosion finally happens, its shockwave plows through this pre-existing debris like a freight train hitting a snowdrift, creating a secondary flash bright enough to rewrite the explosion's entire light curve. The phenomenon was first nailed down with SN 2010 JL, a hypernova in galaxy UGC 5189 that refused to fade normally. 80 days after its discovery, instead of dimming, it suddenly flared brighter than its initial peak. Spectroscopic sleuthing revealed why the blast wave had slammed into a shell of gas equal to 15 solar masses, ejected by the star just years before its death. The collision heated this material to millions of degrees, making it glow fiercely in X-rays and visible light. It was like watching a car crash in slow motion, where the initial impact is just the beginning, and the real spectacle unfolds as debris keeps flying. What makes these bumps so valuable is what they tell us about the star's final years. The timing of the brightening reveals how long before the explosion the material was ejected, while its intensity hints at the wind's density and speed. Some hypernova, like SN 2015 BN, showed multiple bumps, evidence of several violent mass loss episodes. Imagine a star convulsing in its death throes, coughing off giant gas bubbles like some kind of cosmic tuberculosis before the final detonation. These aren't gentle stellar breezes. We're talking about winds so powerful they could strip a nearby planet's atmosphere clean off, the latest twist. Some hypernova bumps suggest their progenitors weren't just shedding material, they might have been engulfed in vast disks of their own making. When the Very Large Telescope studied SN 2017 EU, it spotted a delayed brightening that matched simulations of an explosion punching through a circumstellar disk thicker than our solar system. This wasn't a star quietly aging. It was a bloated, unstable monster, spinning so fast it flung its own guts into space before collapsing into oblivion. Every bump in a hypernova's light curve is like flipping through a star's final diary entries, each one scribbled in panic as the end drew near. For astronomers, these secondary brightenings are more than just cosmic afterthoughts, they're forensic evidence. By decoding them, we're piecing together how the universe's most massive stars spend their final years, not in quiet retirement, but in a frenzied dance of self-destruction, scattering clues across space for anyone patient enough to watch the light fade. Fast radio bursts, those mysterious millisecond flashes of radio energy from deep space, have puzzled astronomers since their discovery in 2007. But one of the most compelling explanations for these cosmic enigmas might trace back to hypernova explosions and the magnetars they leave behind. Here's why: when a hypernova's collapsing core forms a magnetar, it doesn't just create a neutron star, it forges a cosmic powerhouse with a magnetic field so intense it could bend atoms into needle shapes. These fields don't sit idle. They writhe and snap like rubber bands stretched to breaking, unleashing bursts of energy that might manifest as the very FRBs we detect across the universe. The smoking gun came in April 2020, when astronomers caught a FRB erupting from a known magnetar just 30,000 light-years away in our own Milky Way. This wasn't some faint blip from a distant galaxy. It was a full-throated scream from SGR 1935+215, a hypernova remnant so volatile, its previous outbursts had already disrupted Earth's ionosphere. The FRB it produced packed more energy than the Sun emits in 30 seconds, all compressed into a single millisecond. What made this detection revolutionary wasn't just the burst itself, but the accompanying X-ray flare, proof that magnetar tantrums could produce both high-energy photons and radio waves simultaneously. Hypernova prime these magnetars for FRB production in ways ordinary supernova can't. Remember those ultra-relativistic jets we discussed earlier? When those polar beams interact with debris surrounding the newborn magnetar, they create chaotic plasma conditions unlike anything else in nature. Electrons get whipped into spirals by the magnetar's ludicrous magnetic fields, emitting synchrotron radiation that could manifest as FRBs. Some models suggest these bursts occur when the magnetar's crust fractures under magnetic strain, releasing pent-up energy like a seismic snap, only instead of shaking the ground, it ripples space-time with radio waves. Yet the Milky Way magnetar's FRB was oddly faint compared to extragalactic bursts, hinting that hypernova-born magnetars might scale up their violence depending on environment. Younger magnetars, still swaddled in dense hypernova debris, could produce far more energetic outbursts as their magnetic fields battle against surrounding material. This might explain why some FRBs repeat while others don't. The ones we detect from billions of light-years away could be hypernova magnetars in their messy teenage years, while our galactic example represents a relatively sedate adult. The implications stretch beyond mere explanation. If hypernova truly birth FRB factories, then these explosions aren't just about destruction, they're broadcasting their aftermath across cosmic distances. Every time we detect a fast radio burst, we might be hearing the echo of a hypernova's legacy, a magnetar's cry from the grave of a star that died in one of the universe's most spectacular ways. And with every new FRB traced back to a stellar corpse, we're piecing together how the most violent deaths in the cosmos can give rise to some of its most puzzling signals. If the energy of a hypernova were somehow converted into sound, the resulting blast would register at a mind-melting 10 to the power of 44 decibels. That's not just loud, it's a number so absurd it defies any real-world comparison. For context, a rocket launch hits around 180 decibels, enough to rupture eardrums. The atomic bomb dropped on Hiroshima briefly reached 240 decibels, but a hypernova's theoretical decibel level, it's like comparing a single grain of sand to every beach on Earth. Here's the truly wild part: sound that intense wouldn't even behave like sound as we know it. At those energy levels, acoustic waves would distort spacetime itself, vibrating the fabric of the universe like a drumhead. The shock wouldn't travel through air, it would ripple through the quantum fields underlying reality. Forget shattering glass, this is energy sufficient to momentarily warp the geometry of existence. And yet, we'd never hear a whisper of it. In the vacuum of space, sound can't propagate, so hypernova unleash their fury in eerie silence, their violence translated into light, gamma rays, and gravitational waves instead of noise. The physics behind this imaginary soundscape reveals just how extreme hypernova are. Decibels are logarithmic, meaning every 10-point increase represents a tenfold jump in intensity. The difference between a whisper and a jet engine spans about 140 decibels. Now imagine stacking that scale up 44 times. Even the loudest sustained natural phenomenon on Earth, a volcanic eruption like Krakatoa in 1883, barely scratches 210 decibels. A hypernova's hypothetical roar would outclass that by a factor of 10, followed by 41 more zeros. What's fascinating is that while we can't hear hypernova, their energy does create observable vibrations, just not in the way you'd expect. Gravitational wave detectors like LIGO have caught the literal ripples in spacetime from merging black holes, events with energy outputs in the same cosmic league. In a way, those signals are the universe's version of sound, faint echoes of collisions and explosions, translated into frequencies we can measure but not hear. A hypernova's gravitational fingerprint would be similarly subtle, a fleeting warping of the cosmos as its core collapses into oblivion. This thought experiment isn't just about big numbers. It forces us to confront how poorly human intuition handles cosmic scales. We're wired to process threats like thunderclaps or explosions, not stellar detonations where the energy released in seconds dwarfs the sun's lifetime output. A hypernova's sound is a reminder that the universe operates on rules beyond everyday experience, where even the concept of noise becomes meaningless and the most cataclysmic events unfold in perfect, crushing silence. Deep beneath the ocean's surface, in layers of manganese crust that accumulated over millions of years, lies a radioactive time capsule, Iron-60, an isotope so rare on Earth it shouldn't exist naturally. Yet there it is, embedded in sediment layers dating back 2.5 million years, a smoking gun pointing to a hypernova explosion close enough to shower our planet with stellar debris. This isn't just cosmic trivia, it's forensic evidence that Earth has been bathed in the fallout of a nearby hypernova, and the implications are staggering. Iron-60 is forged almost exclusively in the cores of massive stars and scattered into space during supernova or hypernova. With a half-life of 2.6 million years, any primordial Iron-60 from Earth's formation would have decayed into nickel 60 eons ago. Finding it in relatively young geological layers means only one thing: a recent injection from space. Researchers first spotted these telltale traces in deep sea crusts drilled from the Pacific Ocean floor, where Iron-60 concentrations spiked in layers corresponding to the Pliocene-Pleistocene boundary. The same signal later turned up in lunar regolith samples and even fossilized bacteria that had absorbed the isotope from seawater, painting a consistent picture. Around 2.6 million years ago, a stellar explosion within a few hundred light-years drenched the solar system in radioactive stardust. But here's what makes this discovery extraordinary. The Iron-60 distribution isn't uniform, it's concentrated in specific geological strata, suggesting the fallout arrived in distinct waves rather than a steady drizzle. Hypernova, with their asymmetric jets and shock fronts, fit this pattern perfectly. Unlike a spherical supernova spreading debris evenly, a hypernova's focused beams and turbulent ejecta could have sent Iron-60 rippling through interstellar space in clumps, some reaching Earth while others missed entirely. Simulations show that a hypernova just 160 light-years away, potentially from the Scorpius-Centaurus-OB association, a nearby stellar nursery, could explain both the isotope's abundance and its patchy distribution. The timing raises eerie questions. The Pliocene-Pleistocene boundary coincides with minor but measurable shifts in Earth's climate and sea levels, along with a pulse of marine extinctions. While no direct causality has been proven, the math is unsettling. A close hypernova's gamma-ray burst could have partially ionized our atmosphere, subtly altering cloud formation and solar radiation absorption. Even without triggering a mass extinction, such an event might have nudged ecosystems already under stress. It's a humbling thought that the rise and fall of ancient species could bear fingerprints from a stellar catastrophe halfway across the galaxy. For astronomers, these manganese crusts are more than geological oddities, they're interstellar detective work. By mapping Iron-60 concentrations against other isotopes like plutonium-244, which originates in neutron star mergers, researchers can distinguish whether Earth's radioactive visitors came from a supernova, hypernova, or another exotic event. The latest findings tilt toward hypernova as the primary source, thanks to isotope ratios matching models of collapsar nucleosynthesis. Every atom of Iron-60 is a cosmic breadcrumb, leading us back to one of the universe's most violent phenomena and proving that even on Earth we're not immune to the drama of the stars. At the heart of a hypernova, matter doesn't just collapse, it crosses into a realm where physics as we know it starts to unravel. In those final microseconds before a black hole forms, the core reaches densities so extreme that atomic nuclei cease to exist, crushed into a quantum soup where even Einstein's equations strain to keep up. We're talking about conditions so alien, a single teaspoon of this material would weigh more than Mount Everest, collapsing the very rules of space and time. This is where hypernova become cosmic laboratories, pushing matter beyond the limits of textbook physics. As the core implodes under its own gravity, protons and electrons fuse into neutrons, creating a neutron star, an object so dense its surface gravity is 100 billion times stronger than Earth. But in a hypernova, the collapse doesn't stop there. The neutron star's own mass becomes its executioner, crushing itself further until even neutrons can't withstand the pressure. What happens next is where the real mystery begins. Quantum mechanics and general relativity, the twin pillars of modern physics, start to clash violently. At these densities exceeding 5 times nuclear saturation, the core enters territory where hypothetical phenomena like quark-gluon plasma or strange matter might emerge. Some theories suggest neutrons themselves melt, breaking down into their constituent quarks under the strain. Others propose even wilder ideas, like the formation of a Bose-Einstein condensate or exotic states of matter that only exist in the hearts of these explosions. The challenge: no experiment on Earth can replicate these conditions, not even with the most powerful particle colliders. Hypernova are literally rewriting the rules of quantum gravity in real time, and we're left to decode the aftermath. Einstein's theory of general relativity predicts that such extreme densities should create a singularity, a point of infinite density where physics breaks down completely. But nature abhors infinities, and many physicists suspect quantum gravity effects, still poorly understood, would prevent it. Hypernova might be our only window into this no-man's land between relativity and quantum mechanics. When detectors like LIGO catch gravitational waves from massive black hole births, they're not just witnessing a collapse, they're glimpsing the universe stress testing its own laws. The most tantalizing clue lies in the hypernova's jets. These relativistic beams, powered by the core's spin and magnetic fields, shouldn't exist under classical physics alone. Their formation hints at undiscovered dynamics in the quantum foam of a collapsing core, where magnetic fields become so twisted they act like particle accelerators. Some models suggest these fields might briefly stabilize the core against total collapse, buying time for exotic physics to play out before the black hole wins. It's a cosmic balancing act we've yet to fully simulate, because at these energies, even supercomputers struggle to account for every variable. What's clear is this: hypernova don't just destroy stars, they expose the frontiers of human knowledge. Every time one erupts, it forces physicists to confront the gaps in our understanding, from the behavior of matter at Planck-scale densities to the true nature of spacetime under extreme curvature. These explosions aren't just astronomical events, they're nature's way of probing the universe's deepest secrets, leaving behind clues in gravitational waves, neutrino bursts, and elemental abundances. And until we crack quantum gravity, hypernova will remain both the question and the answer, a riddle written in the ashes of the cosmos' most violent deaths. While hypernova are famous for their destructive power, they might also hold the key to one of the universe's greatest mysteries: the origin of life itself. The same gamma-ray bursts that can sterilize planets light years away could have jump-started the chemical reactions needed to build life's earliest ingredients. Picture a nebula freshly seeded with heavy elements from a hypernova explosion: carbon, oxygen, nitrogen floating in a soup of gas and dust. When the explosion's radiation slams into these molecular clouds, it doesn't just heat them. It triggers cascades of chemistry that simpler starlight can't replicate. Laboratory experiments here on Earth have shown something astonishing. When high-energy radiation like that from a gamma-ray burst hits mixtures of water, ammonia, and methanol, common compounds in nebulae, it can produce nucleobases, the molecular letters that spell out RNA. These aren't just random organic molecules, they're the foundational blocks of genetic coding. The process works because hypernova radiation is so intense, it knocks electrons loose from atoms, creating highly reactive ions that drive complex chemical chains. In essence, these explosions act like cosmic chemistry sets, turning simple ingredients into the precursors for life under conditions that would devastate any living thing. The Tarantula Nebula offers a real-world glimpse of this alchemy in action. Within its glowing filaments, astronomers have detected molecules like hydrogen cyanide and formaldehyde compounds that, when zapped with radiation, readily form amino acids and sugars. What's striking is that this nebula houses multiple hypernova remnants, their shockwaves still rippling through the gas. The overlap isn't coincidental. Hypernova don't just sprinkle heavy elements, their radiation provides the energy to stitch those atoms into biologically relevant structures. This paradox destruction birthing creation extends even further. Some astrobiologists speculate that hypernova could solve the homochirality puzzle, why life on Earth uses only left-handed amino acids. When circularly polarized light from a hypernova's afterglow strikes certain molecules, it can break one chiral form more than the other, leaving behind an imbalance. Over millions of years, that bias might explain why life standardized on a single molecular handedness. Yet the most profound implication lies in timing. Hypernova were far more common in the early universe, when the first stars were massive and short-lived. That means the radiation baths needed to forge life's building blocks were abundant just as the first heavy elements became available. It's a compelling case for why life might not be a rare fluke, but an inevitable outcome of cosmic violence where the same explosions that erase worlds could also set the stage for new ones to awaken. Hypernova don't just explode, they reshape entire neighborhoods of space. When these titanic detonations occur in clusters, their cumulative force carves out colossal voids known as superbubbles, cavities so vast they can span thousands of light years, bordered by shimmering walls of compressed gas. Our own solar system floats inside one such structure, the local bubble, a 700 light-year wide pocket of sparse hot gas, sculpted by a chain of hypernova that erupted millions of years ago. The mechanics are as brutal as they are beautiful. A single hypernova's shockwave can blast through interstellar gas like a bulldozer, but when multiple explosions happen in the same stellar nursery, their combined energy stacks up. Each new blast rams into the remnants of the last, pushing shock fronts outward in an ever-expanding sphere. Over millennia, this relentless pummeling clears away dense gas clouds, leaving behind a cavern of million-degree plasma, thin, ionized, and eerily empty compared to the bustling star-forming regions at its edges. The local bubble offers a textbook example. Radioisotope dating of deep-sea sediments and lunar soil reveals a spike in iron-60 concentrations around 10 to 20 million years ago, evidence that a string of hypernova, likely from the Scorpius-Centaurus-OB association, detonated close enough to our cosmic doorstep to excavate this cavity. Today, we drift near its center, surrounded by a ghostly imprint of those ancient cataclysms. The bubble's walls, they're visible in telescopic surveys as glowing filaments, like the Orion Eridanus superbubble, where compressed gas still fluoresces from the violence of those long-ago explosions. But superbubbles aren't just cosmic curiosities, they're galactic ecosystems. By sweeping up gas and dust into dense shells, hypernova create prime real estate for new star formation. The pressure of expanding shockwaves triggers gravitational collapses in those compressed walls, sparking the birth of stellar clusters. It's a self-perpetuating cycle. Hypernova clear space, their debris seeds future stars, and those stars eventually explode to carve new cavities. The Tarantula Nebula in the Large Magellanic Cloud showcases this drama in real time, with multiple hypernova remnants inflating a superbubble so turbulent, it's actively birthing massive stars along its rippling edges. What's wild is how these structures influence life itself. The local bubble's sparse interior lets our solar system cruise through relatively empty space, shielding us from dense interstellar clouds that could disrupt the heliosphere. Meanwhile, superbubbles elsewhere might serve as intergalactic conveyor belts their expanding walls, funneling heavy elements into neighboring galaxies, enriching them with the raw materials for planets and life. Hypernova don't just destroy, they engineer the universe on scales so grand, even their absence becomes a creative force. Not every hypernova gets to fulfill its destiny as a universe-shaking spectacle. Sometimes these cosmic detonations fizzle out midway, not with a bang but a whimper. These so-called failed hypernova represent one of astrophysics' most puzzling anomalies, where stellar collapse stumbles at the final hurdle, producing explosions so underwhelming they barely register on the cosmic scale. The poster child for these cosmic letdowns is SN 2008 HA, a stellar outburst 1,000,000 times dimmer than a typical hypernova, yet bearing all the chemical fingerprints of a cataclysm that almost was. The failure starts deep in the star's core. For a hypernova to achieve its full destructive glory, the collapsing core must strike a perfect balance, imploding just enough to form a black hole while still rebounding sufficient energy to blow the star apart. But in failed hypernova, something short-circuits this chain reaction. Current theories suggest these stars might rotate too slowly, starving the explosion of the rotational energy needed to power relativistic jets. Without that spinning dynamo effect, the newborn black hole simply swallows most of the star's matter before the shockwave can gain traction, like a fire smothered under its own ashes. The result, a muted explosion that barely clears the star's surface, ejecting just a wisp of material at relatively sluggish speeds. SN 2008 HA's oddities don't stop there. While normal hypernovas shine with the light of decaying nickel-56, this event showed bizarrely low nickel production, less than 1% of a typical explosion's yield. Spectroscopy revealed another surprise, an unusually high concentration of oxygen in the ejector, suggesting the outer layers got blown away before the core could fully process its nuclear fuel. It's as if the star started to explode, then changed its mind at the last second, leaving behind a botched attempt at cosmic demolition. Failed hypernova challenge everything we thought we knew about stellar deaths. They hint at a hidden diversity in collapse mechanisms, a spectrum where some stars roar while others barely whisper their departure. For astronomers, these quiet catastrophes are just as valuable as their louder cousins, offering clues about the delicate physics balancing act between black hole formation and stellar explosions. Every failed hypernova is a cosmic what-if scenario, showing us how differently the universe might have evolved if more stars had taken this path, leaving behind black holes cloaked in near silence, their birth scarcely disturbing the interstellar medium around them. The jets unleashed by hypernova don't just fade into the cosmic background, they slice through intergalactic space like celestial scalpels, stretching millions of light years into the void. These aren't gentle streams of particles, they're torrents of matter and energy hurled outward at nearly the speed of light, collimated into beams so precise they could thread a needle across galactic distances. When astronomers peer into the depths of active galaxies, they often spot these same relativistic jet structures so vast, they make the galaxies they originate from look like mere launch pads. The engines behind them, supermassive black holes, or in some cases the hypernova-like detonations of stars so massive, their deaths blur the line between stellar and galactic scale violence. Take the famous Blazar-Markarian 501, its jets visible across radio and X-ray telescopes. Though powered by a supermassive black hole, the mechanics mirror those of hypernova magnetic fields twisted into coils by rapid rotation, accelerating particles to energies that defy earthly physics. The resemblance isn't coincidental. Both phenomena tap into the same universal playbook: collapse, spin, and magnetic mayhem. But while black hole jets persist for millennia, hypernova jets are fleeting, their brilliance concentrated into days or weeks. Yet in that brief window, they etch their signatures across the cosmos. The scale is hard to overstate. A hypernova jet spanning 1 million light-years would extend from our Milky Way to the Andromeda Galaxy and beyond, a luminous filament stitching together the cosmic web. We've caught glimpses of such structures in galaxy clusters, where jets from active galactic nuclei ram into intergalactic gas, creating shock waves that glow for eons. Hypernova jets, though shorter-lived, can leave similar scars. Their particle beams plow through interstellar and intergalactic mediums, ionizing everything in their path and leaving behind radio lobes, ghostly imprints of their passage, detectable long after the light fades. What's astonishing is how these jets retain their focus over such distances. Unlike explosions that dissipate into clouds, hypernova jets stay tightly collimated, their particles locked in parallel trajectories by magnetic fields stronger than any lab-made magnet. This focused energy allows them to punch through galactic halos without dispersing, like a laser beam cutting through fog. Some theorists suggest these jets might even seed intergalactic space with heavy elements, ferrying hypernova-forged gold and uranium far beyond their host galaxies. The real marvel lies in what these jets reveal about universal extremes. When telescopes like Chandra catch X-rays from distant jet collisions, they're capturing hypernova physics, writ large evidence that the same forces governing stellar deaths also sculpt the universe's largest structures. Every time one of these jets flares into view, it's a reminder that the cosmos operates on a continuum of violence, from the death throes of a single star to the engines shaping entire galaxy clusters. Deep in the swirling chaos of a hypernova's collapse, where matter crushes itself into oblivion, the universe might be hiding its most elusive secret: dark matter. Among the exotic particles forged in these extreme conditions, theorists speculate that weakly interacting massive particles, or WIMP, could emerge from the wreckage like cosmic phantoms. These hypothetical particles, long hunted in underground labs and space telescopes, are prime candidates for the invisible glue holding galaxies together. The sheer violence of a hypernova's core, where densities surpass anything achievable in particle colliders, could briefly create conditions perfect for WIMP production, blasting them into space alongside the explosion's visible debris. Actions, another dark matter contender, might also get a boost from hypernova physics. These ultralight particles, if they exist, would arise from the intense magnetic fields twisting through the collapsing star's interior. Picture the hypernova's dynamo-like core spinning at near light speeds as it implodes. Such extreme conditions could twist electromagnetic fields into knots, potentially spitting out actions like sparks from a grinding wheel. Unlike normal matter, these particles wouldn't interact with the expanding shockwave. They'd slip through the ejector unimpeded, carrying away energy and leaving behind a subtle cooling signature in the explosion's aftermath. The smoking gun could lie in hypernova neutrino signals. When detectors like IceCube catch neutrinos from a stellar collapse, they sometimes record slight energy deficits, hints that some energy vanished into invisible channels. If dark matter particles were produced in the chaos, they'd steal energy without leaving a trace, creating gaps in the neutrino data. Hypernova, with their off-the-charts energies, would amplify this effect, making them ideal hunting grounds for such anomalies. The challenge: these particles would flood outward in all directions, impossible to track directly unless they decayed into gamma rays or other detectable secondary particles en route. Here's where things get even wilder. Some models suggest hypernova might not just produce dark matter, they could concentrate it. The jets spewing from the poles could funnel exotic particles into narrow beams, creating temporary dark matter, searchlights piercing the cosmos. If one of these jets happened to point toward Earth, our detectors might catch an anomalous spike in high-energy particles where standard physics predicts none. No such signal has been confirmed yet, but the upcoming generation of telescopes like CTA and the Rubin Observatory could finally spot these ghostly fingerprints. The implications are staggering. If hypernova are indeed dark matter factories, they'd bridge two of astrophysics' greatest mysteries: how massive stars die and what makes up the universe's missing mass. Every time one of these explosions lights up the cosmos, it might be quietly seeding space with the very particles that shape its large-scale structure. And while we can't see dark matter directly, hypernova could be the cosmic breadcrumbs leading us to its source, one cataclysmic explosion at a time. Every hypernova explosion leaves behind a cosmic fingerprint, not just in the elements it scatters, but in the very light it emits. When astronomers train their spectrographs on these cataclysms, they're not just seeing a brilliant flash, they're reading the autobiography of a dead star encoded in spectral lines. Take stripped envelope hypernova, those violent explosions where the progenitor star shed its hydrogen and helium layers before detonating. Their spectra often reveal a peculiar dominance of oxygen and magnesium, elements that shouldn't be so prominent unless the star had bared its fusion-processed core like a cosmic open book. These spectral lines act as forensic evidence, telling us exactly what the star was made of in its final moments. When a hypernova erupts, the intense heat excites atoms in the expanding debris, causing them to emit light at specific wavelengths. Each element leaves its own unique barcode. Iron creates one set of lines, oxygen another, and so on. But here's the twist: the relative strength of these lines reveals how much of each element existed in the star's interior before it blew apart. A hypernova rich in oxygen and magnesium, for instance, points to a Wolf-Rayet progenitor, a star so massive and volatile, its ferocious winds stripped away its outer layers long before collapse, exposing the elemental layers beneath. One of the clearest examples is SN 2003DH, a hypernova whose spectrum blazed with oxygen and magnesium lines so intense they overshadowed expected elements like hydrogen and helium. This wasn't just a chemical oddity, it was proof that the star had died naked, its outer envelopes ripped away by stellar winds or binary interactions. By comparing these spectral fingerprints to models of stellar evolution, astronomers reconstructed the progenitor's life, a star born with perhaps 40 times the Sun's mass, burning through its fuel at a breakneck pace until only an oxygen-magnesium core remained, primed for collapse. But the real treasure lies in the subtler signatures. Hypernova spectra sometimes show peculiar blends of neon, silicon, and sulfur elements forged in the star's final convective pulses before explosion. These aren't just random byproducts, they're snapshots of nuclear fusion's last stand, revealing how the star's interior churned and mixed in its death throes. In SN 2006 JI, astronomers spotted spectral lines suggesting turbulent mixing between layers that should have remained separate, evidence of instabilities that might have turbocharged the explosion itself. What makes these time capsules so invaluable is their precision. Unlike supernova remnants where elements diffuse over millennia, hypernova spectra capture chemistry frozen in the act of explosion. They let us peer into stellar cores without digging through light years of debris, a direct line to conditions no lab could ever replicate. And with each new hypernova decoded, we're piecing together a grander puzzle: how the universe's most massive stars live, die, and ultimately forge the ingredients for everything that comes after. The sheer violence of a hypernova doesn't just tear apart stars, it warps the very fabric of spacetime itself. When a massive star collapses asymmetrically, its lopsided implosion sends ripples through the cosmic continuum, like a pebble dropped into a pond, if the pebble weighed 20 suns and the pond was the universe. These gravitational waves, predicted by Einstein over a century ago, carry the signature of the explosion's chaos, encoding details no light-based telescope could ever reveal. Unlike the clean, symmetrical chirps from merging black holes, a hypernova's gravitational signal would be a cacophony of frequencies, a dissonant chord reflecting the star's final, tortured moments. LIGO, the Laser Interferometer Gravitational Wave Observatory, has already rewritten astronomy's playbook by detecting black hole mergers, but hypernova present a far messier challenge. Their gravitational waves wouldn't ring with the purity of two black holes spiraling in tandem, they'd scream. Picture the core of a dying star, flattening into a disk as it spins at near light speeds before fragmenting unevenly. This asymmetric collapse would jerk spacetime around like a blanket in a hurricane, generating gravitational waves across a broad spectrum. Current models suggest the signal would peak around 100 Hz, right in LIGO's sweet spot, but with overtones and irregularities revealing the explosion's unique geometry. The math behind these distortions is mind-bending. A typical hypernova releases approximately 10 to the power of 46 joules of energy, enough to briefly curve spacetime like a trampoline under a boulder. But it's not the total energy that matters, it's how unevenly that energy gets distributed. If just 1% of the collapse's energy escapes as gravitational waves, a realistic estimate for highly asymmetric events, the resulting ripple would temporarily stretch and squeeze Earth by 1 part in 10 to the power of 21. That's like detecting a hair's width change in the distance to Alpha Centauri. Yet LIGO 4-kilometer arms are sensitive enough to catch precisely that. The catch, hypernova need to be relatively close, within 50 million light-years, for LIGO to spot them. That's why SN 2017 EU, a potential hypernova in galaxy NGC 463, had scientists scrambling. Though no gravitational waves were confirmed, its proximity, just 25 million light-years away, made it a prime candidate. Future upgrades to LIGO and next-generation detectors like the Einstein telescope could change the game. With 10 times the sensitivity, they might catch hypernova waves multiple times per year, turning these explosions into cosmic tuning forks for testing general relativity under conditions no lab could ever replicate. What's truly groundbreaking is what these waves could reveal. The collapse's asymmetry hints at the progenitor star's internal structure, how its layers churned and mixed before the end. Gravitational waves might also expose the exact moment the core becomes a black hole, a transition still shrouded in mystery. Some theories predict a telltale, burst signal as the event horizon forms, a spacetime shudder distinct from the collapse itself. Detecting that would be like catching the universe mid-snap, freezing a frame in the fastest, most violent process nature allows. Beyond pure physics, these distortions carry practical stakes. Hypernova's gravitational waves could help solve the missing heavy elements problem, why some galaxies show more gold and platinum than standard supernova models predict. If asymmetric collapses eject more heavy elements in certain directions, their gravitational fingerprints would point us to where those cosmic treasures landed. It's a reminder that even the universe's most violent acts leave behind more than wreckage. They imprint their secrets onto spacetime itself, waiting for instruments like LIGO to decode them. Every hypernova isn't just an explosion, it's a telegram from the edge of physics, written in the language of rippling dimensions. The race to catch the universe's most elusive explosions is heating up, and next-generation telescopes are arming astronomers with unprecedented tools to hunt them down. The James Webb Space Telescope, with its infrared eyes, peers through cosmic dust to spot hypernova from the dawn of time. Explosions so ancient their light has stretched into faint infrared whispers over billions of years. Already, JWST has identified candidate hypernova in galaxies dating back to just 500 million years after the Big Bang, detonations that seeded the early cosmos with their heavy elements. These observations aren't just about spotting distant flashes, they're time machines revealing how the first stars died, offering clues about the chemical infancy of the universe. But JWST isn't working alone. The upcoming Vera Rubin Observatory, with its colossal 3200 megapixel camera, will scan the entire southern sky every few nights, creating a motion picture of the cosmos where no hypernova can hide. Unlike targeted observations, Rubin's wide-field approach means it'll catch the fleeting afterglows of hypernova by accident, serendipitous discoveries in its relentless survey of celestial changes. Its real power lies in spotting orphaned gamma-ray bursts, those faint, jet-driven explosions where the parent hypernova is too dim to see with current telescopes. By correlating these bursts with Rubin's ultra-deep imaging, astronomers might finally solve the puzzle of how many hypernova go dark, shrouded in dust or dwarfed by their host galaxies. The synergy between these instruments is revolutionary. JWST dissects the chemistry of individual hypernova, studying their spectral fingerprints to decode the elements they forged. Meanwhile, Rubin serves as the ultimate cosmic watchdog, flagging transient events for JWST and others to investigate in detail. Together, they'll map hypernova across cosmic history, from the first stars to modern galaxies, revealing how these explosions evolved as the universe aged and enriched itself with metals. One tantalizing target, the hypothetical population Roman 3 hypernova explosions from the universe's first generation of stars, thought to be monstrous, pure hydrogen giants hundreds of times the Sun's mass. No telescope has ever definitively spotted one, but JWST's ability to detect their predicted infrared signatures paired with Rubin's knack for catching short-lived phenomena could soon change that. Discovering these primordial detonations would rewrite stellar archaeology, showing us how the earliest heavy elements spread through the infant cosmos. The hunt isn't just about the explosions themselves. Hypernova remnants, often too faint for current telescopes, might glow clearly in Rubin's deep exposures or JWST infrared spectra. These ghostly shells could reveal how hypernova interact with their surroundings over millennia, sculpting gas clouds and triggering new star births long after the initial blast fades. Every detection adds another piece to the puzzle, showing how the universe's most violent events became its most creative architects. With these observatories, we're not just waiting for hypernova to announce themselves, we're actively stalking them across space and time, armed with technology that would have been unimaginable just decades ago. The golden age of hypernova discovery is just beginning, and the data flooding in promises to unlock secrets about stellar death, cosmic evolution, and the origins of everything from gold to galaxies. Each new flash in the dark could be the key to understanding how chaos builds the universe we know today. Ancient stargazers didn't have telescopes or satellites, but their meticulous records of celestial events might hold clues to hypernova witnessed millennia ago. Take the famous guest star of 1054 AD, documented by Chinese astronomers, a sudden light in the sky so bright it was visible during daylight for 23 days before fading. While modern science classifies this as the supernova that birthed the Crab Nebula, re-examining other historical accounts reveals anomalies that don't fit typical stellar explosions. Some descriptions, like the Korean record of a 1066 AD event lasting months with rays like a fan, mirror what we'd expect from hypernova afterglows. The sheer duration and luminosity of these ancient sightings suggest explosions beyond ordinary supernova, possibly hypernova mistaken for divine omens by pre-telescopic cultures. One tantalizing candidate lies in the Aboriginal oral traditions of Australia's Wardaman people, passed down for generations. Their stories describe a great flame in the Coalsack Nebula region, an event they called the Fire Star. Modern radio surveys of that area reveal something striking: the remnants of a stellar explosion dating back roughly 30,000 years, with chemical signatures hinting at an unusually energetic blast. The Wardaman account details a light that burned bright as day for weeks, aligning with hypernova models predicting extended visibility due to shock-heated debris. Unlike fleeting comets or nova, these prolonged events etched themselves into cultural memory, preserved through songs and rock art. The challenge is separating hypernova from more common phenomena in ancient texts. Chinese court astronomers meticulously logged celestial events, often differentiating between Bushui sudden stars and Huixing broom stars, likely comets. Some entries defy easy classification, like the 1264 AD report of a star near Eta Carinae that shone with 5 colors for over a year. Eta Carinae, a volatile binary system capable of producing a future hypernova, sits in a region where isotopic studies suggest a past cataclysm. Could this have been a hypernova witnessed 7 centuries before telescopes? The duration matches modern observations of hypernova light curves, where radioactive decay and circumstellar interactions prolong visibility. Even Europe's medieval chronicles offer potential clues. The Anglo-Saxon Chronicle describes an event in 774 AD where a crucifix appeared in the heavens after a strange star. Modern analysis of ice core samples from Greenland and Antarctica shows a spike in radioactive beryllium-10 around that time, a telltale sign of enhanced cosmic rays, possibly from a nearby stellar explosion. While supernova can produce similar isotopes, the abrupt onset and religious interpretations hint at something more dramatic: a hypernova's intense gamma-ray burst interacting with Earth's atmosphere, creating luminous atmospheric phenomena mistaken for divine signs. The real breakthrough may come from combining archaeology with astrophysics. Japanese researchers recently reanalyzed 8th century Mokkon or wooden tablets used for imperial record-keeping, discovering references to an unsettling red star in 792 AD that coincided with tree ring anomalies indicating a spike in cosmic radiation. Planetary nebulae in that direction show unusual concentrations of titanium-44, an isotope primarily forged in hypernova nucleosynthesis. These interdisciplinary threads weave a compelling case. What ancient cultures witnessed as portents might have been the universe's most violent explosions, their light stretching across centuries to reach us not just as photons, but as stories etched in bone, bark, and stone. What's remarkable is how these records endure. The Aboriginal fire star, the Chinese 5-colored light, Europe's celestial crucifix, each could represent independent glimpses of hypernova, their brilliance transcending language and culture. In an age without spectroscopy or imaging, our ancestors still captured the essence of these cataclysms, not just points of light, but transformative events that lingered in the sky and the human imagination. Today, as we cross-reference ice cores, tree rings, and oral histories with satellite data, we're not just rediscovering lost explosions, we're reclaiming a cosmic heritage written in the stars and remembered by those who first saw them flame to life. The chilling power of hypernova hasn't just captivated scientists, it's fueled the nightmares of storytellers for decades. From blockbuster films to best-selling novels, these cosmic cataclysms have become shorthand for ultimate annihilation, their sheer scale offering a canvas for apocalyptic fiction. Take Disney's The Black Hole, where a spacecraft races against time to escape a hypernova's lethal gamma-ray burst, a plot twist ripped from real astrophysics, albeit dramatized. The film's fictional Cygnus hypernova mirrors actual fears. A nearby explosion's radiation could strip away Earth's atmosphere, turning our planet into a lifeless husk. Sci-fi thrives on these worst-case scenarios, but the reality is stranger than Hollywood's imagination. Where fiction often gets it right is the hypernova's asymmetry, those deadly jets. The Three-Body Problem trilogy by Liu Cixin weaponizes this concept, depicting an alien civilization using a hypernova's focused beam as a galactic-scale death ray. The science holds up. Real hypernova do channel energy into narrow polar streams, those spanning light years rather than targeting planets. Other works, like Interstellar, flirt with hypernova physics indirectly. While the film's Black Hole, Gargantua, steals the spotlight, its backstory implies a hypernova-like collapse, with time dilation effects echoing the relativistic chaos near these explosions. Yet for every accurate detail, creative liberties abound. Star Trek, Discovery once stranded its crew near a hypernova remnant emitting chronoton particles, a technobabble twist on the real magnetic turbulence these events leave behind. Even Doctor Who's The Impossible Planet amps up the drama, portraying a hypernova as a sentient force hungry to consume reality. These fictional takes prioritize spectacle over precision, but they're not entirely unmoored from science. The 2012 thriller Seeking a Friend for the End of the World hinges on an Earth-killing hypernova, tapping into genuine astrophysical debates about extinction-level stellar explosions. What's telling is how these stories reflect humanity's primal awe of cosmic forces beyond our control. Hypernova embody the universe's indifference, a reminder that existence could be rewritten in an instant by events unfolding light years away. Sci-fi amplifies this existential dread, but the truth is no less staggering. Unlike asteroid impacts or supervillain schemes, a hypernova's threat can't be thwarted by heroes or technology. It's a humbling narrative device, one that underscores how fragile our place in the cosmos truly is. The genre's most poignant twist, some stories hint at hypernova's creative potential. In Alastair Reynolds' Revelation space series, ancient alien civilizations harvest hypernova remnants for exotic matter, turning destruction into opportunity. This duality, catastrophe and genesis, mirrors reality, where these explosions seed galaxies with life's building blocks. Sci-fi's doomsday scenarios may dominate, but the deeper truth lingers. Hypernova don't just erase worlds, they set the stage for new ones to rise. So next time you see a film's sky split by a CGI hypernova, remember, the real thing is out there, shaping the universe in ways no screenplay could fully capture. From the incomprehensible power of a hypernova's gamma-ray jets to the ancient stardust in your jewelry, we've journeyed through 30 mind-bending facts about the universe's most violent explosions. These cosmic cataclysms don't just destroy, they forge, shape, and even spark the building blocks of life itself. Imagine a single explosion outshining entire galaxies, or a dying star scattering gold across the cosmos. Picture shockwaves carving stellar nurseries from chaos, or gravitational ripples warping spacetime itself. And lurking in the aftermath, magnetized stellar corpses with magnetic fields so strong they could erase Earth's data from halfway across the galaxy. But the story doesn't end here. Behind every hypernova lies a deeper mystery waiting to be unraveled. Which fact left you breathless? Was it the discovery of iron-60 in ocean crusts, proof of a nearby explosion millions of years ago? Or the eerie possibility that a hypernova's gamma rays might have jump-started life's chemistry? Drop your thoughts below. We're diving into the comments to geek out over your favorites. And stay tuned, because next time we're tackling magnetars, the universe's ultimate cosmic dragons, spinning silently in the dark with enough magnetic fury to twist atoms into needles. Until then, keep looking up. The cosmos is far stranger than fiction.